Welcome to lecture number 29. So today we are going to revisit some of our basic knowledge regarding vectors that we have learned back in our high school. So vectors are very important, right? So they define force, velocity and momentum, etc. Okay. And in the context of quantum mechanics, we would be studying this momentum quite a bit. So in that respect, since momentums are nothing but vector quantities, we have to learn some basic properties of vectors. So today we are going to concentrate about the algebraic way of representing vector. Okay, so when we talk about vectors, we go back to our basic concepts of the Cartesian coordinates. So I can draw a Cartesian coordinate system, x, y, and z. Okay, and this is the origin here. Now let's imagine that a vector, this vector is called A, and this is represented as A over and sign of arrow over A. Okay, so how we write the vector A? So in algebraic way, there is a way to write the vector A, because what we do, we resolve three components of that vector along three mutually perpendicular axes x, y, and z. While we do so, we define some unit vector along x, y, and z. For example, I becomes unit vector along x, j becomes unit vector along y, and similarly k becomes unit vector along z. So we choose I, j, k as per the definition. Okay, and then what we do, that we then calculate or we consider the components of A along x, y, and z. So for example, if we take the component along z axis, so for example, let's think that this is AZ. Okay, so AZ becomes the magnitude of that component along z direction, and k is the unit vector. Similarly, this towards, then we take the projection along xy plane, and we have the components along x becomes ax, and component along y becomes ay. So therefore, the whole vector can be represented as the magnitude ax along x direction multiplied by the unit vector I plus ayj plus azk. Alright, this is simple. And then what if we think about another vector b? Alright, so let's imagine there is another vector b where the components along I, j, and k directions are bx, by, and bz respectively. So we can similarly represent, bxi plus byj plus bzk. Alright, so these are the two vectors, so I can also draw that vector b over here. Okay, so now the thing is, let's quickly come into our context. So to come to that, let's quickly recollect the addition of vectors. So how we used to add vectors? How did we learn that? Okay, so the addition of vectors, that is a plus b. Okay, then if we add those two, what we have to do is we have to add up the components or the magnitudes along x direction. Okay, so we do it like ax plus bx multiplied by I, and then plus ay plus by multiplied by j plus az plus bz multiplied by k. Okay, so this becomes the algebraic way of representing an addition of vectors. Okay, so I hope that this much thing is clear now. So very quickly, we now would proceed to the multiplication of vectors. Now in multiplication of vectors, there are two ways where you can multiply the vectors. So that means the definition of the vector products are of two types. One is the scalar product and another is the vector product. So let's quickly refresh our memories about the scalar product and the vector product. Okay, so here we go next. Okay, so now we first start discussing about the dot product, or it is also known as the scalar product. So by definition, I have again written the two arbitrary vectors that we have started with, vector A and vector B. So these are defined like this. So the product between A and B, so it is okay, represented as A dot B. All right. So of course they are vectors. So we can write like this: A dot B is equal to the same thing as B dot A. So it doesn't matter which vector you pick first, whether it is A or B. So that becomes equal to the modulus of A, that means the magnitude of A, the magnitude of B multiplied by cos theta. So theta is the angle between A and B. So if this is the case, then you can imagine that I dot I is equal to value of j dot j is equal to k dot k, and those are unit vectors. Okay, so unit vectors means, so between I and I, so these are basically the same vector. That means they're lying along the same direction. So for them, theta is equal to 0. So this becomes I dot I, okay, is equal to j dot j is equal to k dot k. All right. So basically, this becomes 1 because theta 0 is equal to cos theta is equal to 0. So that value becomes 1. So because we define that I squared is equal to 1, or j squared is equal to 1, or k squared is equal to 1. All right. So then I dot j, okay, is equal to j dot k is equal to k dot I, whatever. The angle between those two, theta, is equal to 90 degree, pi by 2. So cos 90 degree is 0. So that means the dot product between two mutually perpendicular directions is basically 0. All right. And also, if we take that equation A plus B, and if we take the dot product with another vector C, so it becomes A dot C dot plus B dot C dot. Okay, so this is another equation for this. And now what I'm going to do is, let's take the product of A dot B here in this case. Okay, so if we take A dot B, what do we get? Now you see, there are 3 terms and there are 3 terms. So 3 multiplied by 3, so there should be 9 terms. Okay. Now you see, out of 9 terms, some of the terms will become 0 because we have this I, J, J, K and Ki. All right. So can you tell me how many terms will become 0? So out of the 9 terms, you will see that 6 terms would become 0. Okay. So that means there would be only 3 terms left. So what are those 3 terms? The terms, those are like I, J, J and K terms. Okay. So this should be going to be AX, BX plus AY, BY plus AZ, BZ. Because you understand that I dot I, J dot J, K dot K would become is equal to 0. Alright. Now this also tells me that if I do A dot A, okay, if I do A dot A, then what we have is basically AX square plus AY square plus AZ square. Okay, and A dot A we can also take as the mod of A square. Okay, so that means whatever the magnitude of A, we are taking the square of it, and similarly we can try to determine the value of A. That means the modulus value of A, the magnitude of A becomes whole root over of ax square plus ay square plus az square. All right. So these are the pretty basic features of the dot product or scalar product of the vectors. Okay, and we have represented the two vectors A and B like this. Okay, so I hope you are now very familiar with this. So now let's move on to the cross product or the vector product of the vectors. Okay, so let's continue. Okay, so now let's quickly talk about the cross product or the vector product. So here are the, once again, my two basic vectors A and B by standard definition. So the cross product is defined as like this, A cross B, okay? And the magnitude of it, because this is a vector quantity, so there is magnitude and direction. So the magnitude of this A cross B is defined as modulus of A multiplied by modulus of B multiplied by sine theta, where theta is the angle between A and B. And remember that if you write A cross B, so this is not equal to same as B cross A. So the B cross A becomes actually, so we can write like this, A cross B is equal to minus B cross A. So which vector you select first during the multiplication, that becomes important. So that would define the sign. Why is it so? Is it because the direction is defined by something like this. So this is A vector, this is B vector, and this forms, means the cross product forms a right-handed system. So where the direction of the cross product A and B is always becomes the perpendicular over the AB plane. So this is the AB plane and the angle between them is the theta. Alright, and so we right-handed system, right? So we go like this. That means, so if we swipe my thumb along the AB plane or the plane of the board, so the vector becomes perpendicular of it. So this represents my A cross B. Okay, so the direction becomes the A cross B. So this is the direction of A, this is the direction of B. So similarly, we can now define that what could be the value of I cross I. So you see that between I and I, the angle theta is 0, so sine 0 is 0. Okay, so I cross I is 0. Similarly, J cross J is 0 and K cross K is 0. So now what happens? I cross J. Alright, so if this is I and this is J, so you can imagine that if we apply the cross product, so the resultant vector means the product would be perpendicular to I and J, so that has to be K. Alright, so similarly we can derive the other things, but for that we have to remember that we have to make a little sign like this. Okay, we can make a small circle and we can write I, J and K, and we can draw this clockwise direction, some arrows. Why? Because I and J would give you K, alright, but the moment we write J and I, so J cross K would give you minus, sorry, J cross I would give you minus K because you go against the direction. Okay, so the same, so in similar fashion we can write that J cross K is equal to I, alright, K cross I is equal to J, alright, but the moment we write K cross J, it becomes minus I, alright, or the moment we write that I cross k, it becomes minus j. So something like that. So you have to remember this small little diagram of ijk along this clockwise direction, and remember this would go a cyclic manner. Okay, so as long as you are following the circle, I cross j becomes k, k cross I, j cross ki, something like that. And the moment you go reverse, there would be a negative sign associated with it. Alright, so now what we are going to do, the last thing, we are going to take the cross product of these two vectors, a, b. So that means we are now going to find out what should be the value, or basically the magnitude of a cross b. Remember, it has three components, it has also three components, and some of them will probably vanish because I cross I 0, okay, and some of them would not vanish. So how we can do that? All right, so I think let's clean the board and work it over freshly so that we can easily follow what is the cross product of a and b. Okay, so let's do it. Now to perform the cross product for a set of vectors like a and b, as we have written previously, as a memory aid we can represent the cross product in the form of a determinant. Okay, so this would help us to formulate how easily we can perform the cross product of two vectors. Okay, so that means we have to write this in a determinant form where at the top I can write those three unit vectors I, j and k, and then at the very bottom I write the three components of a vectors along I, j and k respectively. So it becomes ax, ay and az, and for b I write the same, bx, by and bz. Now this makes so easy to find the final product. How? So once we evaluate this determinant, so we have to do like this, I multiplied by this determinant, we have ay, az, okay, and by, bz. Hope you remember this from your high school days. Now we have minus j. Why the minus sign? Okay, probably you can now recollect. Ax, az, and bx, bz. Okay, plus we have k and the remaining determinant like ax, ay, and we have bx, by. Okay, very good. And then we have to find the final product over here. Okay, so let's do it over here. We have I multiplied by, from left it will go left diagonal, aybz, minus the right diagonal, azby. Now it doesn't matter whether you write az first or by first, it absolutely doesn't matter. Okay, and then minus j axbz minus azbx, okay, plus k multiplied by axby minus aybx. All right. So now here you can see that we have a negative sign here and also a negative sign. So let's flip it. So let's make everything as positive. So now the resultant vector becomes y multiplied by aybz minus azby, okay, plus j. I can write azbx minus axbz plus k axby minus aybx. Okay, so this now becomes the resultant cross product. Okay, so you would see automatically it has taken care of those I cross I, j cross j, and k cross k terms, because those were, those became 0. So basically, if we keep out 3 terms out of those 9 terms, it would now becomes 1, 2, 3, 4, 5, 6 terms. Okay, so this is how, so this is the magnitude of the cross product of A and B, and this is how easily we can perform the vector product of the two vectors A and B. Alright, so now let's move on to the vector momentum. Okay, so first we'll talk about a little bit of the linear momentum, then we will move on to the angular momentum, that how an angular momentum vector and its components can be represented based on the knowledge that we have gained so far. Okay, so let's clean the board and start over again. Okay. Okay, so here we talk about the momentum, both linear and angular momentum. So let's first talk about the linear momentum here. Okay, so as you see, I have written this operator for momentum. So P, operator P is equal to minus IH cross. You can easily identify the sign and the operator. Yes, the square of it called the Laplacian operator. And this represents the momentum in 3 mutually perpendicular directions. So I del del x plus j del del y plus k del del z. Okay, so now the linear momentum P can be represented as is a summation of Px plus Py plus Pz. Okay, and similarly, we can write that momentum is equal to mv. So linear momentum, so we can write it as mvx plus mvy plus mvz. So it's needless to say that px, py, pz and vx, vy, vz are the velocity vectors along x, y and z, that is 3 mutually perpendicular directions. Okay, so now here we talk about the angular momentum L. So the angular momentum L is defined as the cross product of two vectors R cross P. Okay, so what is R? R is the position vector and P is the momentum vector. So the position vector R is represented by this. Okay, so once again we draw mutually perpendicular Cartesian axis x, y and z, and let's imagine that this is the point, this is the magnitude of vector R. Okay, and its coordinate is x, y and z arbitrarily. So this is a particle, so remember there is a particle. So the particle was at a coordinate x, y and z, and it is represented by the vector r, and this vector r, the magnitude is through the origin, means from origin, with respect to origin, this x, y, z is defined. Okay, so therefore we can represent the vector r as ix plus jy plus zk. So needless to say that I, j and k are the 3 unit vectors. Okay, so therefore now we have to take decide the cross product of L, that is the R cross P. Now before we go, once again we also define this quantity B is equal to dr dt. Okay, because this r, okay, because the particle is moving, so its velocity is dr dt. So once again, the dr dt can be represented as I dx dt plus j dy dt plus k dz dt. All right, and similarly, So therefore, we can write these things as this part as Vx, so we can write as I Vx plus J Vy plus K Vz. Okay, so now we can identify these here Vx, Vy and Vz. Okay, so this becomes is equal to, basically now we can think about that is Vx vector. Okay, so this is represented as I Vx. So now we can now write that P once again, okay, is equal to, similarly we can write IPX, okay, plus JPY, or okay, let's represent it. Okay, so let's consider this one, P is equal to Px, Py plus Pz. Alright. So now we have to come back and we have to take the expression. We have to evaluate the value of this cross product. So how we can define the cross product? So we now have defined the R vector like this, P Ix plus Jy plus Zk, and now also we have defined the momentum vector P as Px plus Py plus Pz. So basically we have to take the cross product. How? Just before a few minutes ago, we have seen that by using the determinant, we can find out the cross product. So using the same knowledge, we are going to find it out. Okay, so let's do it. Okay, so here is the expression of R vector and here is the expression of P vector, and we are considering the cross product of the two. So we again go by the rule of determinant. So I, J, K, and then X, Y, Z, and then Px, Py, Pz. Now if we do so, and if we evaluate the determinant, you will see that we will have these three components along with multiplied by I, multiplied by J, and multiplied by K. So therefore, the resultant, the cross product, that is called the angular momentum L, then it can be resolved into three mutually perpendicular directions. These are Lx is the component along x direction, Ly is the component along y. Similarly, that is for Lz. So if L is represented by this, then from the product of these vectors R cross P, we can easily identify that Lx is this, Ly is this, Lz is this. So this simply came from the cross product. Okay. So if you go back to the postulates of quantum mechanics, where we have checked various operators. Okay. So probably you remember that you have seen that Lx, the operator Lx, it's the angular momentum along x direction, was given by this expression ypz minus zpy. Okay, so at that time it appeared a little bit difficult for us that how an Lx operator will be represented like this. So you can still go back to the list of the operators in your textbook and find out what are the expressions of Lx, Ly, and Lz. So you will find exactly that was the expression. So today we have now discussed the basis, that how these operators Lx, Ly, Lz, how those expressions came from. So bottom line is that those are the three components of the net angular momentum L. Okay, and corresponding operator is definitely L cap. So now what would be the direction of the L? Okay, the direction of L would be definitely the perpendicular to the plane of R and P. Okay, so once again, if we have this vector R and if we have this vector P, then L becomes perpendicular to R and P. Okay, sorry, so according to our definition, as what we have seen earlier, we should be drawing like this. This is R and this is P. Okay, so this is the right-handed system. So L becomes perpendicular, the direction of L becomes perpendicular with respect to the R and the P plane. Okay, so this little lecture today gives us enough background to understand what are the expressions of the components of angular momentum, that is Lx, Ly and Lz. Alright, so in next chapter we will be learning more about the properties of these individual components Lx, Ly and Lz, whether these components commute with each other or not, and few other exciting properties. Okay, so we will see you in the next lecture. Till then, goodbye.